Hi, I'm Shawn Yoshida, and today I'm going to be talking about single particle tracking. And so like the name implies, single particle tracking is basically the process of following the motion of a particle as it moves around. The way we collect data is usually on a microscope with some set frame rate of maybe 25 or 33 or something like that hertz per second, keeping in mind that it needs to be sufficiently fast to actually capture the location of the particle at enough frames to put together a trajectory. And we'll end up with some movie that shows the motion of the particle or particles. And from there we can generally get diffusive information or information about diffusion. So whether that's actually just identifying different diffusive species or if it's seeing if there's some flow in some set directions, it's a very versatile tool. And it seems pretty straightforward, but there are three main problems that we run into, and we'll go over each of them. One is low signal-noise ratio, which just means that we can't actually pick out the particles from the noise. One is the diffraction limit, which we'll discuss a bit more, but and then the last one is the problem of multiple particles with potentially overlapping trajectories. All right, so the first issue is that signal-noise ratio, picking the particles out of the noise. So on the left here we have a representation of what our data might look like without any kind of signal-noise ratio enhancement, and it's very difficult to tell where the particles actually are. And if we can't tell where the particles are, it's impossible to actually track their motion. So the first thing we need to do is figure out how can we get from this left to the right where we know exactly where the particles are. There are two main methods that people tend to use. One is spot detection. And spot detection relies on an Aucher wavelet transformation decomposition, which is unfortunately very computationally expensive, but it works very well. So we get very good signal-noise ratios, aka infinite signal-noise ratio. The downside is it takes a very long time. So if you have many particles or a very long movie, you probably want to avoid spot detection. The other option is local averaging. And like the name implies, it's taking some set neighborhood and then averaging the intensities at that local area. And this can be faster, but it does have an improved signal-noise ratio, maybe double, rather than infinite. And it is also dependent on what local area you choose, so whether it's 2x2 pixels or 3x3 pixels, etc. So after this, we can now pick out the particles from the noise. Our next step is to solve that diffraction limit issue. So briefly going over what the diffraction limit is, it's defined as lambda over 2 times our numerical aperture, which is the range of angles over which our lens can collect light. So if we have a green laser and a numerical aperture of, say, 1, which is fairly standard, for biological applications, this is going to be about 250 nanometers, which means if we have two objects closer than 250 nanometers, we can actually resolve them. So for our purposes, what that means is if we have a particle, rather than seeing one particle, we're going to get this Gaussian surrounded by airy disks. And so rather than just seeing one, if we look at it from the side here, it might look more like this, where we have higher order maxima and minima, but really we want the particle to be here. And the two ways we can solve for this are by fitting to a Gaussian, which is, again, computationally expensive but accurate. The other option is by exploiting radial symmetry. So we know that this 3D Gaussian is radially symmetric, no matter which direction we come at it from. And so this is slightly less accurate, but it is much faster. And so now we can actually localize the position of the particle. The last step is to calculate the trajectories. So like I mentioned earlier, our movie will have one, or in this case, I guess 2 particles that are moving around, and one might be moving faster than the other. We might end up with something like this. How do we know which path they're following? And so the two methods we have here are nearest neighbor, which is very common. And essentially nearest neighbor will just take the nearest particle and then assume that that's the tracked particle. The other option is these more global methods, which basically calculate every possibility. So we'll calculate these guys too, and then figure out statistically or probabilistically which one is the most likely. And again, nearest neighbor is fast, but has, I say inaccurate, but it's more inaccurate compared to global methods. And global methods is very slow, but more accurate. And accuracy in this case just means we have a higher or lower chance of false linkages. And so that's single particle tracking. We basically have the motion of a particle. We increase the signal noise ratio. We localize the location of the particle if it's too small, and then we calculate the trajectories. And then from there, depending on your sample, you can get diffusive information about different diffusing species or overall flow, etc. Thank you for listening.